Well, hello everyone. Thank you so much for the invitation. I'm really honored. And I'm also really honored sharing my particular domain of research, which is astrochemistry. And that's why I'm going to give quite like an introduction to astrochemistry and then talk a little about my specific research, even though sometimes I'll make some mentions of what I'm interested in myself for my research. A little bit about me. So I think that was a great description. I'm born and raised in France, and okay. And I did my undergrad and my master in chemistry over there before I moved to Boston for my PhD. And fun fact, I'm doing my PhD in astronomy, and I've never done any astronomy courses before coming doing my PhD, which was tough. But I'm a 6 year and I'm gonna defend my thesis this August. So it's coming soon. And I had the chance to be in a really great group, which, as you can see in the pictures, is mainly composed of women, which I think is really unique in the field of astronomy. And so that's something I like to point out. And that's the people that helped me grow through my PhD. Okay, but I'm going to do some introduction. I guess that when you look at the sky, the objects you can think about are black holes, stars, planets, or even maybe some objects you don't even know what they are. In my case, what I'm interested in is not as big as those objects. And that's actually extremely tiny. And that's something you can have in your house. It's dust. And that dust is the same dust as you can have on the floor, which is made of carbon and silicon. And that's what we have in space. And here you're observing an actual image showing just a cloud of dust. But first, I want to do just a little side knowledge, which I think is fun. I think most of you might know, most of you not, but it just to give a little insight, which is electromagnetic spectrum. Electromagnetic spectrum is different ranges of observation. As human, we can see in a visible range, which is here. But telescope has the ability of looking at specific ranges that will give us really important details in astronomy. And here I'm not going to talk about, I'm not going to talk about Earth-based telescope. The next images will come from space telescope. So no Earth one yet. And as an example, I'm showing you a cloud of dust, which has been taken with the Hubble Space Telescope here. And you can see that the range of the Hubble telescope is some visible and some infrared. And on the left-hand side, you can see the visible range of a cloud. And on the right-hand side, the same cloud with the same position, but done with infrared. And it's really nice to look at the comparison because you can definitely see the different details that we have in each images. And one thing that I'm pointing out on the right image is that the cloud feels like more thin, and the ability of looking at infrared is that we can actually see what the cloud is made of when we use infrared spectroscopy, because we can see the star and the background object shining enough to give us some transmission to the telescope. Oh, okay. But that was just a side. What I'm interested in is the places where star and planets form. Star and planets form through 4 main stages, with the first one just being a cloud of dust. In this cloud of dust, your particles gonna start accreting to each other at the point to be like this cloud. It's kind of like a chimney. And when the particles are so close, they're gonna collapse and create a new star, which is our second stage. This new star is going to be a little smaller and it's gonna be really warm with really high temperatures at the point that those particles gonna go from the solid to the gas phase. But because we started from a cloud, we still have the rest of that cloud, and that's why we have a disk, and now it's a disk of dust. Through time, we're going to the third stages, which is a planet-forming disk, where the star is more settled, the power is more regulated, and here we have a disk of the remnant dust, where planets going to be able to form in, to then go to the last stages, which is the planetary system. But just for fun, and I think that looking at images is always nice, I'm going to show you actual images taken for each of those stages. So first, the molecular clouds. So that's the same image as before, a little lower quality, but I did it voluntarily just to really accentuate those clouds, which are chimney-like. And what's funny is that it's always been represented as a cloud. And the reason is because space is never empty. We always have dust around, but they are so far from each other that they can't attract. They only attract through millions of time until the point where gravity does its job and form the star in one of those chimney. So when we go to the second stage, the new star, which here's an illustration of a new star where we can see the star in the middle and the jets. I think it's easier to say the jets going from both sides where the dust gonna go into the gas phase, but we still have the cloud around, which is really dense. And so when we look at an image, we do see the jets properly on both sides of our star, but the cloud around can't be seen. And the reason is because the cloud is so dense that no objects in the background can actually emit enough energy for the telescope to actually observe what's in the cloud. And that's actually a problem in our field. That's something really common. It doesn't only happen to that second stage, it happened to any stages, depending on the type of clouds you are actually observing, because thousands of cloud has been found in space, but a lot of them are really hard to see. First reason, which is the cloud being really dense. The second reason is the position of the disk. Because if the disk is flat, you're just passing by your disk, and so you can't observe it, which is really hard to find perfect candidates. But here we're just looking at picture, and thankfully that's not what I'm doing, so it's nice to just talk about it. But I wanted to show what a data processing look like for that stages, because it's really unstable, but I don't want you to spend too much time on it. It's just to show both sides, the images to the process data. Then we're going to the planet forming disk, or the place where planets gonna start forming. On the right, we have a sketch of it where we can clearly see the planet forming, while on the left, we see the data processing, which is clearly the same disk that you can see on your right. And it's a really nice resolved image, which in few slides, we can get a lot of details from it. Something that I would like to point out at that stage is because the star is centered in a disk, you can expect the temperature being really warm close to the star and super cold toward space. And planets do have preferences of formation. And that's something actually we can observe in our own solar system, where how the planet towards the end of our system is colder. And funny as it is, study has shown that planet will prefer to form closer to those colder places before moving toward the sun. A few papers, as mentioned, it. And the reason is chemistry, but that will come up. Okay, and finally, the planetary system, where it's simply almost our solar system, but with differences depending on where the planets form in the previous stage. And the reason is because where the planet is forming, it's not going to accrete the same materials. But here are some of the biggest questions in our field we're trying to answer, which are we alone and how do we get here? But we can divide those big questions in smaller questions. And then I was like, okay. But yeah, the main questions are there other Earth-like planets out there? If life was out there, could we make contact? And what other planet exists? But then the second biggest question, how did we get here, is related to how do planets form? How do we get the ingredients of life? And how do we stars form and evolve? But particularly, I'm more interested in that part, which is how do we get the ingredients of life, which is where the chemistry comes into the story. And so if we need the ingredients of life, then we need to have chemicals present in all those stages. But it's really hard to track just because what are those chemicals? But if you remember, I told you about dust. And I'm really putting it at the singular, one dust, which I think makes the whole difference. Because one dust hosts multiple particles or multiple chemicals at the surface of that dust. And so if you go back to our stages, if a dust ends up having so many molecules on its surface, that means that even starting at the molecular cloud stage, we're having way more chemical than we could have think of, which means that those chemicals is going to have different stages as well, which means for each stages, we have different energical processes that will enhance or destroy the chemical present on those dust. But thankfully, we know that Earth in space is the only place that has evolved chemical. But for the story, it's not consistent, right? Because how can we go from the beginning to the end of our personal story? Well, thankfully, our solar system has comets. Comets is a great place to have other chemicals on it. And comets, and you can trust me on this, uh, is the remnant material from the formation of our solar system. And the reasons of that is because if we look at our solar system and the scale of it, comets are at the end. And from what I said before, what's closer to the sun is warmer, so it's easier to desorb from the solid to the gas phase more easily, while comets are so far away that they actually don't desorb any chemical except with some specific cases. But comets are really the pristine of our different stages of star and planet formation. So far, what has been thought is that the comets and the chemical from the comets are from the molecular cloud. But here's why astrochemistry is important, is because we're proving that it's not only simple molecule here, but we actually have even an evolution of processes, chemical, physical, but the chemistry itself evolving through the stage, because that has never been done before. And here just a picture of a surface of a comet, which is 67P. I don't know if you're familiar with 67P, but 67P is the first mission where they send a rover on the surface of that comet to get some samples. But that mission failed because when they sent the rover couldn't land. But thankfully, it succeeded to trap some molecule during its journey around and a little bit on the comet. And so they were able to observe what they think is the pristine of our solar system. And for a long time, and it's still a discussion that we could even like talk about afterwards, it is believed that those icy bodies, so comets or even asteroids, came on Earth to distribute this variety of chemicals. But what I'm particularly interested in is how can we make this molecule in space and how common are they? And as I said, space is not empty. We have dust everywhere. It's a really broad way to look at it, but it's true. It's just that this dust is not the same depending on the time scale. And we can observe it really well. We can observe it really well. And something that came up is that we did have proof that water is actually formed on those dust. And water is the main component of space. Water is the main component, and then you can think as carbon monoxide being the second main component, but only at 60% compared to water, which is not necessarily that much. And that paper has been incredible in our field because our field is quite recent. I would say that the first paper came out in 1970s. So it's a really new field. And so little progresses, thanks to observation, leads us to better understand the chemistry and our history. So that's why I wanted to introduce the dust and the fact that happened in our field. And as I said, we have our dust, and on the surface of it, we have those molecules. I think that sketch is great because you can see that the molecules are not close to each other. They're actually pretty far. And it takes millions of years for one simple chemical reaction to happen because they're so far and they need time to move. The way you can illustrate the dust, I think it's a really good way, this one. And I'm sure you think about this molecule when I'm telling you at the surface, like a dust and just molecule around. Well, it's not wrong. You have two states, so solid and gas, possible. The dust cannot go in a gas phase except in extreme temperature. While temperature, it's really easy to be in the gas phase. Also because it's only on the surface of the dust. So in space, you have two ways to have molecule. The first one is to be in the gas phase because it has desorbed from the dust. And the other one is in the ice phase, which is literally you have your dust and you have an ice coated around your dust. And that ice is mainly composed of water and carbon monoxide, mainly. And to give you an insight, those regions are minus 440 Fahrenheit, which is really low. But we need those temperature to have chemistry happening. I'll not go further in chemistry, but if you have questions, I'm really happy to talk about the process that happen on those surfaces because it's definitely not the same kind of chemistry as the one we have on Earth because liquid phase doesn't happen in space. And so we use ground telescope to observe. It's quite nice, actually. We have really nice results with Earth telescope in terms of the first stage, the second and third stage, I would say. And space telescope will be more useful for the first stage and for the clouds in general, just because they're so thick. And if we have the atmosphere on Earth, we can't deal with both. So we use space telescope mainly for those ones. Okay. But you might wonder, I can't stop talking about molecule, and that's true, I only said two so far, but you can wonder how many molecules are there in space. Well, a lot. We have more than 330 molecule that has been detected. And when I say detected, it's detected with telescope, so with our processed images. And I will not go further in the detail of detection. I'm happy to talk about it, but because I want to keep it kind of broad, uh, I want to be open for questions since I don't know how many of you heard about that field. Something to point out with those molecules is that those molecules are small. And the way I talk about small is because of atoms. So as you can see on top, I have the number of atoms for each molecule. So when I talk about atoms, I'm just thinking about like one oxygen, one hydrogen, and another hydrogen to make water. And in space, it's really rare to have molecule more than 10 atoms. The one that has been detected with more than 10 atoms has been usually found on comets, which is amazing because comets tells us that we have really long molecule, which in a way you can relate to DNA. I mean, we need a lot of molecule to create DNA or RNA. But in space we have nothing, which means that we do miss a gap in between to understand how more complex molecule get formed. And here just a molecule that I like, which is in space, which is alkyl formate. You have its representation here. And it's a molecule that tastes like raspberries and smell like rum that we have in space. And my advisor can't stop saying that it smells rum in space. And I think it's a fun fact to know. Okay. So if we go back to our stages of star and planet formation, we actually realize that way more molecules are present than we thought before. And because we're observing so many molecules, I can tell you that what we see on comets do not fully correspond to what we observe. So when we have the statement of comets is the pristine or the inheritance of our molecular cloud, it's actually not true. It's the inheritance of the molecule that went through all those stages. And when I'm saying going through all those stages, I'm not necessarily thinking about a certain molecule here that will still be there at the end, but we're gonna have a lot of transformation. Like starting from a water, we can have an alcohol, so a molecule of alcohol. And from the alcohol, maybe we can start having a little bit more complex molecule that could be related to beginning of DNA, which is crazy, right? And that's also crazy because it's a fact that not everyone admit yet. And that's why laboratory experiment is important. And I am an experimentalist. I work in the lab, so I do not do observation, but I use observation as a motivation to understand those stages. So in our lab, we're gonna have those ultra high vacuum machines. So if we take the example of this one, here just what we call a chamber. And within this chamber, we're gonna have really cold temperature and really low pressure that can mimic the space, literally, but with less debris. We still have a lot of assumptions when we work in the lab, but the lab has proven being efficient with observation when we compare data. And so that's what I do. That's me on an everyday work routine. And you can see that I was getting tired since my hair are going all over the place. To give you an insight, an experiment takes 1 day. And I think that my first paper, I had to run, I think, 203 experiments to properly publish my first paper. And in that paper, I only had something like 60 experiments in it. So that's a lot of time. But funny, it's still a lot of fun for me. And that's something that in the lab I'll continue doing. Here is a 3D sketch of one of our experimental setup. And briefly, we have the main chamber. And the main chamber is where I can create the ice. And around, I have 2 ways of analysis. One is infrared spectroscopy, which is the same thing that Space Telescope does, and I can compare if I want to, but I don't have to. The other one is what we call a mass spectrometer, and it records any difference when my ice goes from the solid to the ice, from the solid to the gas phase. So that I can know at any moment what kind of molecule I have all the time in that chamber. And I did a mistake. This is not minus 275 Fahrenheit, it's minus 440 Fahrenheit in the chamber. And as a reference, the pressure is extremely low. We have 10 to the minus 9, 10 to the minus 9, 10 to the minus 10 in our chamber. While on Earth, we have 800. I do not put unit voluntarily, just because here it's a comparison. It's not something to remember. And so if you have to think about the ice, here is our grain. And on the surface of our grain, we have some ice. In the lab, we can control what that ice is. We can put any molecule that we want, any molecule that we want to target. And we can make that ice as thick or as thin as we want. Here is the inside of one of our experimental chamber. And what you have to look at is here. This is a sample holder. And on top of it, we have our ice. So you could see the sample holder being the dust grain. And this really faint whitish thingy is the created ice on it. And so that's a typical day that I have in the lab. And as a chemist, I am doing nothing with chemical reaction. I just connect the molecule that I'm interested in, and I put all of it in my chamber, and I just look at the results, which is different because we have to respect the conditions.
You should drink less coffee.
Sorry?
You should drink less coffee.
Yeah, I know. It takes a long time to run an experiment and to set everything properly. Here's another sketch, just in case to give you a little bit more detail and being more familiar with what an ice is. So we have our dust and we have the ice around. This ice can be any molecule, but usually we try to respect what we have in observation with what the more common molecule we have. So we have water, carbon dioxide, we have carbon monoxide, methane, and I'll not say more. And what's great is that literally in the lab, we can reproduce what we can do in space. So we have different energetic processes like UV irradiation to actually irradiate the ice and see what's happening. And then through observation, we can look at from point A to point B of my experiment, vs stage 1 to stage 2, for example. And if I start with just water and CO, for example, looking if it's stage 2, I have the same products as I have in my experiment. And it looks like really minimum, because how can we compare lab to observation? But it actually really is useful. Thanks to the James Webb Telescope, for the first time ever, we can actually observe ICES. So it's only been 2 years that my work is actually relevant to the astrochemistry community on a big scale. And that has been um, pretty exciting. And here just another video. So in the previous one, I was showing you how to settle the molecule. Here is just a way to manage our setup. I think that one is less coffee. That one, I think I've been reasonable on coffee. But what we do literally is just to respect what we can mimic in space by cooling everything down and then setting everything. And here just another sketches of the picture I showed you before, where here is our sample holder that can represent the dust and our ice, and literally what a star can do on our ice. Okay. And even though we see maybe more than 400 molecules now, every year we just have more and more detection of molecules, which I think will not stop thanks to the James Webb Telescope. We have so many data to process. The James Webb has been able to found multiple objects of those stages. And because each object has particular signature of molecule, we can better understand the story of somehow the origin of life, but just the origin of molecules. Thank you. Oops, sorry. If you have any questions, I'm really happy to answer.
I got a million questions.
That's great. I like questions.
What kind of vacuum system are you using to get -10 scale vacuum?
We're just using a really powerful pump, vacuum pump, and
Turbo?
yes,
Is it a turbo pump?
exactly, a turbo pump.
My question, Alexia, is how goes the search for the components of DNA in your research?
I would just say that we're looking more at which atom are necessary for life production. So, for example, nitrogen, I would say, is one of really the main one.
Yeah.
So, if we talk about lab oriented, we're gonna try to either look at the formation of certain nitrogen bearing molecule, or we can do a destruction of it to see how it can be started with. And I also forgot to mention that there is I don't remember the name because it's not what I'm doing especially, but there is a nitrogen bearing molecule on the comet 67P that has been found, which is one of the molecules that is necessary for life. And it has been successfully reproduced in the lab for, I think, one of the first, probably the second or third time in our lab. We have this machine that reproduce meteorites. And so that's how we can kind of like now get the sample out of it and then do more like earth chemistry with like liquid phases to better know if we do have these multiple atoms, molecules.
Thank you. Good to know.